Hello and welcome to Angle Shot Projectiles. In this video we're going to talk about all the different important positions along the trajectory of a projectile that is launched at an angle. We'll start by taking a look at this diagram over here. So in this diagram you see that I have a projectile that's going to be launched at some starting velocity, which I'm going to call V0 or V0, at some angle above the horizontal. And the path that we take, we know, is going to have a parabolic shape to it. So I'm going to go ahead and draw that in there. And I'm going to go ahead and identify 4 important positions that we're going to talk about here throughout the flight. The first position we're going to talk about is what I call point A. And point A is the launch position. Up here, point B is going to be when we reach its maximum height. Point C, which it's not going to be really important in this particular case, but point C is when we get back to the starting height. Now in this case, because we do have a horizontal part of our motion, we will have moved horizontally by the time we get to C, but we're back to the starting height. And finally, way down here at the bottom, when we are just about to hit the ground, we are going to call that point D. Now do keep in mind that when we do hit point D, we're not talking about what happens after the object hits the ground. We're talking about what happens as the object is hitting the ground. This is still a free fall type problem. We're going to be using 9.8 meters per second squared as our acceleration in the vertical axis. And because of that, once the ground comes in contact with the object, or vice versa, we're no longer in free fall. So the problem stops once there's actually contact made with the ground and our object feels that force. So here are the 4 points that we are going to be talking about. And over here on the left, what I'm going to do is I'm going to kind of break it down and talk about each of these positions, what we can do at these positions, and different things that we know or we can deduce about these positions. So point A is our launch position. All right, now, what's going to happen here is going to depend on the problem, but 9 times out of 10, if not more than that, you're going to be given this V0, this starting velocity, and that angle. So what you're going to do, knowing your vector basics and your trigonometry, we are going to be able to figure out that our horizontal velocity is going to be equal to that starting velocity times the cosine of that angle. So your horizontal velocity, we're going to be able to calculate. Likewise, the vertical velocity at this point, but that is going to be at the beginning. So this is going to be my initial vertical velocity. I call that VIY. I would not suggest calling it VI, because in reality, this right here, what I'm calling V0 or V0, is really the initial velocity. That is, how fast is it going at the very beginning. This quantity right here represents how fast it's moving vertically only. And that, of course, V0 sine theta. So once again, you see, we're using cosine to figure out a horizontal component. We are using sine to figure out a vertical component. And just in case you need to see that broken down, I'm going to magnify this vector here and say, here's my V0. And here are the 2 components of that triangle. All right, so you'll notice that Vx, the horizontal side, is adjacent to my angle, hence using cosine over here. VIY, the vertical portion of this initial velocity, is opposite the given angle, hence using sine in this case. All right, so that's what we know at point A. There's not a whole lot else that we can do because really nothing's happened yet. I'm going to move on to point B next. And the significance of point B is that we are now at our maximum height. All right, so if you recall, you've probably done just plain toss-up problems when you were just talking about free fall and throwing things straight up into the air. And there was a situation in those types of problems that was very similar to this, where you got to that maximum height. And some things that we know at this point are as follows. Well, if you recall, when you got to the maximum height of a toss-up problem, the velocity at that point was 0. Now, what are we going to call that velocity? That's where we have to be really, really careful, because once again, we now have both horizontal and vertical motions happening simultaneously, all being put together to make this one path that we see. So this is definitely the vertical velocity at this point. So I'm just going to say Vy equals 0. Now, you might look above here and say, well, up here you called it Viy. Does that mean that this would be Vfy? And the answer to that is maybe. Because sometimes we are just going to focus on the very first portion of this flight, how long it takes and how far it goes in going from A to B, in which case this would be the final vertical velocity. But there might be a situation where you might want to actually start at B and focus on from there all the way down to the ground, and that definitely does happen, in which case we could call that the initial vertical velocity. So what I'm going to do here is I'm just going to say Vby. So I'm going to say that's the vertical velocity at point B. Whether you call it the initial or final would depend on the context of the problem that you're working on. All right. Now, at B, the other important things that we need to know here have to do with time first. Why did I just write velocity? That doesn't make any sense. The time that it takes to get to B is 1/2 the time that it takes to get to C. So you'll notice here that the time that my object rides, the distance that we rise from A to B is equal to the distance that we fall from B to C. And since they both are going to have the same acceleration of 9.8, which I haven't really mentioned yet, we know that the time for A to B would be equal to the time to B to C. Therefore, the time that it takes to go from A all the way to C would be exactly double the time that it takes to get to B. The other thing that we know here is my horizontal displacement at B, and I just use D for displacement in case you're confused. If you use delta x or some other symbol, feel free, is also 1/2 of our horizontal displacement at point C. So these are important things to know, because when you do get to point C, very rarely will you ever focus on point C when trying to solve a problem. Most of the things that a problem would ask for at point C, you can figure out by simply solving for things at point B and then doubling them, as you see with these two relationships here. All right, so moving right along, now we go to point C. So point C, we have now returned to the height that we were at point A. So we returned to our starting height. The things that I'm going to write here at C are basically the same things that we had at B, just kind of turned around. So the time here is double the time at B. This is one that we use all the time. Very, very, very common. Also, horizontal distance or displacement at C is going to be double that at B. All right. In addition, the velocity is going to be the same as V0, except I'm going to put a negative here in parentheses. The difference is we are now going to be falling at the same angle. So the speed is the same. So if I knew that this speed here was 10 meters per second, we'd be going 10 meters per second here. The only difference is, instead of traveling at an upward angle of theta, it would now be at a downward angle of theta, and it would look something like that. I missed it somehow. So this would still be theta. All right, so this negative in parentheses is basically implying that the negative applies to the angle being downward. The magnitude of that velocity is the same as it was at launch. The only difference is the direction. All right, it's not exactly opposite, so it's not really appropriate to say really negative. So I'm going to put that negative in parentheses with a little asterisk there, and I'll put a little asterisk here. All right, so there we have it for point C. Moving right along to letter D, here where we have to be real careful with some things, all right? So at point D, we don't really know a whole lot, all right? But in most problems, this height right here is going to be given, all right? So my displacement at point D is going to be equal to negative that height. And that negative sign is really, really important. And after you take a look at this video, I hope you'll look at some of the problems that I have posted here as well that basically work through problems involving angle shot projectiles off of a cliff. And in some of those videos, I actually go through and make some obvious mistakes in forgetting negative signs so that you can see what's going to happen if you were to forget those negatives. So why is that negative? Well, in our vertical axis, we're going to be considering up to be positive, down negative. So since the object ends up below where it started, the displacement at that position is negative. The other thing that we need to keep in mind is as follows. The vertical velocity at D, which you could say is final velocity here if you wanted to, because it is the end of the problem. There's nowhere else that it could be after that, so it's definitely going to be a VF anytime you're going to talk about it, is also negative, right? I don't have a numerical value here, but I'm just going to point out that it is downward. And the reason that that trips up so many people is because 9 times out of 10, when you solve for this velocity, when you solve for the vertical part of this velocity, you end up using this equation over here. And to solve for VF, guess what the last step that you do is algebraically, right? The last thing you do is square root it. You plug that into your calculator, you hit square root, and your calculator is just going to spit out a positive number. What you have to keep in mind, and this is really cool because, you know, these little rules that your math teacher throws out every once in a while, and you're like, yeah, but why? I don't really care that it can be negative. You know, here's a situation, a real life situation where the negative answer is actually the answer. So when you take that square root, you have to choose to use the negative value, all right? If not, when you use that velocity to then calculate the time, for example, everything's going to get all screwed up. All right, so there you have it. Now, but I had never mentioned that your acceleration, which I think you already know, and of course this is your vertical acceleration because there is no horizontal acceleration. Your vertical acceleration is 9.8 meters per second squared downward. I'm not going to put a negative sign in front of that because that will depend on the context of what you're doing. Sometimes you'll have that be a positive value. Sometimes you'll have that be a negative value. And that should do it. Actually, one more thing before I go ahead and let you guys run with this. The reason, or one of the reasons that I go ahead and give these letters and identify these is because frequently in these problems, you're going to be asked a number of different things. For example, you might be asked, what is the maximum height at B, right? If they asked you that question, you would use variables. You would use quantities, things that you know between points A and B. You wouldn't care about what happened after point B, right? So you would make a list, a little XY chart, identifying the things that you know horizontally and vertically from A to B. The problem is, what if in part B, the second part said, what is the time in the air, right? Well, the time in the air doesn't stop at B. It keeps on flying, right? We can go all the way down here and land at the ground below, and the time is going to be much greater than it was at B. So now all of a sudden, you care about the whole flight, A to D. So why is that important? Because you have to realize that the variables that you used to solve the first part of the problem can't be used to solve the second part of the problem. A few of them might, but not all of them. So each time that you're focusing on a different part of the flight to solve a different part of your problem, you're going to have to go ahead and start with a new list of givens. All right? Oh, and by the way, I didn't mention this at the beginning, but the reason I have this dotted line here is to identify your starting height. But sometimes these angle shot problems are not off of a cliff or a building. Sometimes they're along level ground, like if you're kicking a football at the beginning of a game, right? In which case the problem would end right there at C. So sometimes problems do end at C, but if you're going off a cliff or off a building or so forth, the problem will take you all the way down there to letter D. All right, I hope that helps. Good luck.